I am Chandramohan, Director of Erudite Coaching Center. Today I am introducing the electromagnetic theory. The topic is the static fields in free space and air. Okay. So, in this topic, there are some important areas on which questions can be expected in TAFR, PhD and integrated PhD entrance exams, just CSIR, JRF, GATE physics, and also other national level MS entrances like JNU Delhi, Hyderabad Central University, Banaras Hindu University, etc. So, some of the important areas are the solutions of Laplace and Parson's equations, boundary value problems, and multiple expansion. Then the other important areas are problems based on the boundary conditions of electrostatic fields. Okay. So, here I am discussing one of the important topic, that is the multiple expansion. Here we are discussing about the approximate potential of a charge distribution at large distances. Let us take some arbitrary charge distribution. Okay. Some arbitrary charge distribution. Here in the figure I have shown a volume charge distribution having a charge density rho of r prime. Okay. The speciality here is the arbitrary charge distribution which I have considered may have a net charge or its net charge may be 0. What is the example of a charge distribution whose net charge is 0? It may be a linear quadrupole where you can see, right, okay, 4 charges which are arranged on the z-axis, okay, right, symmetrically about the origin O, okay, and for this, what is the net charge of this charge distribution? 0. Now coming to the dipole, physical dipole, okay, right, where the two equal opposite charges minus q plus q are placed on z-axis, right, okay. For this, what is the potential? Or you can consider some arbitrary charge distribution whose net charge is not 0, non-zero value. Here in these two examples, the net charge is 0, net charge is non-zero, right, okay. So, I considered a charge distribution, a volume charge distribution having charge density rho of r prime, okay, rho of r prime. Then for this continuous charge distribution, the potential, right, is given by 1 by 4 pi epsilon naught volume integral rho of r prime into d2 prime by r, okay, where r is the separation vector from the source point to the field point. I took a volume element d2 prime here, okay, this is the volume element in this charge distribution, and the position vector of this source is given by the primed vector r prime, and the field point P is represented by the position vector r, okay, right. And using cosine rule, you can relate the separation vector r and r prime, okay, separation vector r and position vector r and r prime, okay. So, right, okay, what is the relation you have from cosine rule? R square is equal to r prime square plus r square minus 2r prime cos theta prime, okay, right. So, using this, right, 1 by separation vector r, right, becomes 1 by r into sigma n is equal to 0 to infinity r prime by r whole power n into Pn of cos theta prime, okay. That means the value 1 by separation vector r is, right, acting like a generating function for these legendary polynomials Pn of cos theta prime, okay. And substituting this in the above equation 1, okay, right, substituting 2 in 1, we are getting the potential of this arbitrary charge distribution, okay. V of r is equal to 1 by 4 pi epsilon naught sigma n is equal to 0 to infinity 1 by r power n plus 1 integral r prime whole power n into Pn of cos theta prime into rho of r prime into d2 prime. Means you are getting a series of terms for this charge distribution. When you are writing the potential at some point P, okay, you are getting a series of terms, and this series which you are getting is called multiple expansion. It's called multiple expansion. Okay, so right, for this charge distribution, when you are writing the potential at point P, right, it is having a contribution from several terms. Okay, what are those terms? Before going in detail, first of all, right, let us see for a physical dipole, what is the potential at the point P? It is q by 4 pi epsilon naught r plus minus from this charge, okay, q, small q, right, okay, q by 4 pi epsilon naught r minus. Using cosine rule, you will get r plus and r minus. Substituting here, finally you will get v is equal to p dot r cap by 4 pi epsilon naught r square, where p is the dipole moment of this physical dipole, charge into length of the dipole. Okay. Then for a linear quadrupole, right, okay, where the charges are arranged on the z-axis, okay, symmetrically about the origin, right, at a distance d, this positive charge plus q is there, at the origin minus 2q is there, right, and at a point on the negative z-axis below, right, plus q is arranged. This linear quadrupole, right, when you are calculating the potential at point P, then V is equal to q by 4 pi epsilon naught into 1 by r1 minus 2 by r plus 1 by r2. When you simplify, substituting r plus r minus values from this cosine rule, using cosine rule, you will get q a square, okay, or q d square, sorry, q d square by 4 pi epsilon naught r cube into 3 cos square theta minus 1. That means for this charge distribution, although the net charge is 0, the potential is not 0. For this charge distribution, although the net charge is 0, okay, right, but the potential is not 0. Okay, therefore, right, okay, for any charge distribution, okay, right, whose net charge may be 0 or may not be 0, right, the potential is given by this expression, okay, right, whose special cases are shown here, right, okay. In general, this series, right, given by equation 3 can be expanded and can be written like this, which is called multiple expansion, equation 4, okay. So here the first term, where when you put n is equal to 0 here, right, you will get the first term. When you put n is equal to 1 in equation 3, you will get the second term, right, and this first term is called monopole term, and when n is equal to 1, it is called dipole term. When n is equal to 3, it is called quadrupole term. When n is equal to 4, the fourth term is called octupole term, and so on. Like this, right, we got a multiple expansion. Right, here basically it is used as an approximation scheme. Okay, right, when you want to calculate the approximate potential due to this charge distribution at large distances, okay, right, then the lowest non-zero term in this series gives the approximate potential at large distances. Okay, suppose if the monopole term is the non-zero term, then it gives the approximate potential at large distances, right. Okay, the other terms will only add to improve the approximation scheme. Suppose if the monopole term becomes 0, right, then the lowest non-zero term may become dipole term, okay, right. Then this dipole term gives the approximate potential at large distances, okay. The other higher multiple terms will only improve the approximation scheme, okay. Like this expression will give you the approximate potential of any charge distribution at large distances, right. Now coming to the monopole term. The first term is the monopole term. When you put n is equal to 0 in equation 3, you will get the 1 by 4 pi epsilon naught r into volume integral rho of r prime into d2 prime, and right, okay, we are writing this as q by 4 pi epsilon naught r. What is q? Q is the net charge or monopole moment of the charge distribution, right. Integral, volume integral rho of r prime into d2 prime is the net charge or the monopole term of the charge distribution. Okay, this monopole term, right, is the dominant term. Okay, if it is non-vanishing, this is the dominant term, right, in the contribution to the potential, and it gives the largest, right, it gives the largest contribution to the potential. Okay, if it is non-vanishing, then this term gives the approximate potential at large distances. Okay, right. Now, for example, if you take a point charge at origin, right, if you take a point charge q, right, capital Q at origin, okay, then, right, okay, at a point P, right, it gives the, right, q by 4 pi epsilon naught r gives the potential. But now when the point charge is at origin, okay, it acts like a pure monopole. Why? Because right, for this, right, okay, point charge at origin, right, only one term will be there, okay, that is q by 4 pi epsilon naught r. All other higher multipoles vanish, become 0, right? No dipole term, no quadrupole term, all higher multipoles will vanish. That means a point charge at origin acts like a perfect monopole, okay, a pure monopole, right? Okay. So for that, right, only the approximate potential formula becomes the exact potential, okay, and no other higher multipoles come into picture, okay. Now coming to the dipole term, right, the second term, when you put n is equal to 1, right, in this equation 3, you will get the second term dipole term, okay, 1 by 4 pi epsilon naught r square into r prime cos theta prime into rho of r prime into theta prime. In this r prime cos theta prime, where theta prime is the angle between r prime vector and r vector, therefore it can be written as the dot product of r cap dot r prime. What is the value of r cap dot r prime? It is nothing but r prime cos theta prime, okay. So therefore, right, integral r cap dot r prime into rho of r prime. You are doing integration on primed coordinates, therefore this r cap can be brought outside the integral. So r cap by 4 pi epsilon naught r square dot integral r prime into rho of r prime d2 prime. Now this quantity is now defined as the dipole moment of the charge distribution, okay. The monopole moment of the charge distribution is this, the net charge, whereas the dipole moment of the charge distribution is P is equal to volume integral r prime into rho of r prime into d2 prime. This you have written, dipole moment you have written for volume charge distribution, right. Accordingly, right, if the charge distribution is continuous charge distribution, is a surface charge distribution, then how to write the dipole moment? P can be written as surface integral r prime into sigma of r prime into dA prime, okay. If it is a surface charge distribution, then the dipole moment is given by this expression. If the continuous charge distribution is a line charge distribution, then line integral r prime into lambda of r prime into d2 prime, okay, right. So for all continuous charge distributions, now I have written the dipole moment. Now if the charge distribution is not a continuous charge distribution, if it is a discrete charge distribution, then this expression can be written as sigma P is equal to sigma I qi prime into ri prime, okay, sigma I qi prime into ri prime, okay, where qi are the discrete charges, okay, ri primes are the position vectors of those discrete charges, okay. So if the charge distribution is a discrete charge distribution, then the dipole moment of that charge distribution can be expressed like this, okay. So this is about the dipole moment of continuous charge distributions and discrete charge distributions. Now one of the important area which is asked in the entrance exams, he will give some discrete charge distribution, he will ask you to calculate the dipole moment of that charge distribution, and he will ask, right, will this dipole moment depends on the origin of coordinates or not, okay, or, right, he may give you some continuous charge distribution, okay, and he will ask you to calculate the dipole moment of that charge distribution, right, okay, and he may ask you, will this dipole moment depends on the origin of coordinates or not, okay. Origin of coordinates plays a very important role in the multiple expansion, okay. Just now I explained, okay, monopole moment is nothing but the net charge, okay. Therefore, right, the monopole moment or the net charge does not depend on the origin of coordinates, okay, right. Whatever may be the origin of coordinates, the monopole moment of the charge distribution, which is nothing but the net charge, does not depend on the origin of coordinates, okay, right. Now if a point charge is placed, right, at the origin of the coordinates, then it acts like a pure monopole, right, and whose potential is given by V is equal to q by 4 pi epsilon naught r, where q is the point charge which is placed at the origin. The same point charge, right, okay, when it is shifted from the origin, right, okay, it is shifted from the origin, then, right, okay, its potential is given by, right, V is equal to q by 4 pi epsilon naught r, okay, q by 4 pi epsilon r. Now this 1 by r acts like a generating function for legendary polynomials, right, and you will get again a series of terms, okay. So when the point charge is at the origin, it is behaving like a pure monopole, but the same point charge is shifted from the origin, okay, is shifted from the origin like this, okay. This is the origin of the coordinate system. Now the point charge is shifted, okay. The point charge is shifted now, okay. So when the point charge is shifted, then what happens? This is the field point, this is position vector r, and this is your separation vector r, and this is your r prime, okay. So this is theta prime, okay. The same figure I have shown for, okay, a point charge, right. Now, right, okay, at this point P, what is the potential due to this charge? Right, Q by 4 pi epsilon naught r, okay, Q by 4 pi epsilon naught r, separation vector r, okay, Q by 4 pi epsilon naught separation vector r, okay. Then what is happening? V is equal to Q by 4 pi epsilon naught separation vector r, okay. Again that 1 by r, 1 by separation vector r is equal to this 1 by r into sigma n is equal to 0 to infinity r prime by r whole power n into Pn of cos theta prime. Means what is happening? 1 by r is acting like 1 by separation vector r is acting like a generating function for legendary polynomials, and you are getting a series of terms, okay. So when a point charge is at origin, it acts like a monopole, okay. It has only monopole contribution, right, monopole term, and all other higher multiples vanish. Then in that case the approximate potential becomes the exact potential, but the same point charge is shifted from the origin, okay, or the origin is shifted, okay, right. Charge may be shifted or origin may be shifted. Then what is happening? Now the potential is given by, right, V is equal to Q by 4 pi epsilon naught separation vector r, okay, Q by 4 pi epsilon naught separation vector r. Now that 1 by separation vector r is giving you a series, okay, this series, right, okay, when it is substituted here, you will get this, a series of terms. Now not only monopole term, right, it includes dipole term and all other higher multiple terms. That therefore a point charge at origin acts as a pure monopole. A point charge, right, okay, shifted from origin is not acting like a pure monopole, it is also having higher multiple contributions. So therefore origin of coordinates plays a very important role, right, in multiple expansion. Now coming to the dipole term, okay, right. In case of dipole term, okay, the dipole moment, right, depends on the origin of coordinates, okay. Generally the dipole moment depends on the origin of coordinates, okay, right. If the origin is shifted or if the charge distribution is shifted, then the dipole moment generally changes, okay. But there is an exception, okay, right. There is an exception. If the net charge of the charge distribution or if the dipole moment of the charge distribution becomes 0, then the dipole moment, right, okay, does not depend on the origin of coordinates, okay. Similarly, right, the quadrupole moment of the charge distribution, right, depends on the origin of coordinates, okay, right. But there is an exception. If the net charge or monopole moment and also the dipole moment are both zeros, then the quadrupole moment does not depend on the origin of coordinates, and so on, okay, right, for octupole moment and so on. So therefore, right, the dipole moment, the quadrupole moment, the octupole moment and all other higher multiple moments generally depends on the origin of coordinates, but the monopole moment, which is the net charge, does not depend on the origin of coordinates, right. Now I will take up some examples where I will try to calculate the dipole moment of some charge distributions and what is the role of the origin of coordinates, right, on those dipole moments. Let us see now. Two problems which illustrate the calculation of the dipole moment, one in case of discrete charge distribution, another in case of continuous charge distribution. So this is a problem where we are calculating the dipole moment of this discrete charge distribution, and then after calculating the dipole moment, we are also finding the potential and field at a point quite far off from the charges, okay. Some in the same plane, we are taking some point which is very far from the charges. Now the charges are at the vertices of the hexagon A at corners B, C, D, E and F, right. Charges minus Q, plus 2Q, minus 2Q, plus Q, minus 2Q and plus 2Q, okay. Here for this, what is the monopole moment net charge Q? right, it is 0. Okay, so therefore, right, the monopole moment is 0. For this, right, we have to calculate the dipole moment. Okay, the monopole term is a vanishing term, therefore it will not contribute to the potential. So the approximate potential at far off point, right, whatever potential he has asked, it is given by the dipole term. Monopole moment is 0, net charge is 0, monopole moment 0, no contribution from the monopole term. Now we are calculating the, right, for the dipole term. Okay, now right, we are using the formula for a discrete charge distribution. P is equal to sigma I Qi prime into Ri prime. Okay, so right, in this case Ri prime is only x cap into xi prime plus y cap into yi prime. Therefore, you will get only Px, that is sigma Qi into xi, and Py sigma Qi into yi. That's all. So using it, Px minus Q into x1 a, right, then 2Q into a by 2, then minus 2Q into minus a by 2, then plus Q into minus a, then minus 2Q into minus a by 2, then plus 2Q into a by 2. Finally, what is the value we are getting? Here 2 is cancelled, minus QA plus QA is cancelled, then 2 is cancelled, plus QA minus QA cancelled, 2 is cancelled, plus QA, total 2QA. Then coming to the y component of the dipole moment. Okay, here 0 into Q 0 plus 2Q into root 3 by 2a minus 2Q into minus root 3 by 2a minus 2Q into minus root 3 by 2a. Okay, then plus Q into 0, then minus 2Q into minus root 3 by 2a, minus 2Q into minus root 3 by 2a, then plus 2Q into minus root 3 by 2a. Okay, so plus 2Q into root 3 by 2a minus 2Q into minus root 3 by 2a, right? Okay, then minus 2Q into minus root 3 by 2a, 2Q into root 3 by 2a, minus 2Q into minus root 3 by 2a, then minus 2Q into minus root 3 by 2a, then plus 2Q into minus root 3 by 2a. This minus a by 2, here minus root 3 by 2. Okay, so minus 2Q into root 3 by 2a, so this will get cancelled. Okay, then this and this will get cancelled. Okay, so total it is 0. Okay, therefore, right, P has only x component, 2QA into x cap. Then potential, right, okay, of this contribution, right, dipole contribution is P dot r cap by 4 pi epsilon r square. You got P 2QA into x cap by 4 pi epsilon r cap, x cap dot r cap. Okay, in case of this plane polar coordinates, it becomes cos theta. Okay, right, 2QA into cos theta, where x between x cap and r cap, this is x cap direction, and you are taking some point far off, and this is r direction. Between r cap and x cap, the angle is theta. Therefore, 2QA into cos theta by 4 pi epsilon naught r square in plane polar coordinates. Then electric field, because this potential formula is a coordinate free form, right? Okay, any coordinate system you can apply, right? And now using right the potential formula, we are writing the electric field. Electric field is the negative of the potential gradient. Electric field is the negative of the potential gradient. Therefore, it is how much in spherical coordinates? Minus dou v by dou r into r cap, minus 1 by r into dou v by dou theta and theta cap, minus 1 by r sin theta into dou v by dou phi into phi cap. But this potential of this charge configuration consists of only theta and r terms, no phi terms. So the phi component is 0, phi component is 0, phi component is 0, but we have to evaluate the r component of the electric field. So differentiating this with respect to r minus dou v by dou r, you will get this, right? Differentiating this with respect to theta, you will get E theta is equal to minus 1 by r into dou v by dou theta, that is 2 qa sin theta by 4 pi epsilon r cube. So we have written the electric field also, and electric field finally E is equal to ER into r cap plus E theta into theta cap. Okay. So this is 4 qa cos theta by 4 pi epsilon naught r cube into r cap plus 2 qa sin theta by 4 pi epsilon naught r cube into theta cap. Okay, this is the electric field of this charge distribution. Now coming to the next problem, we are calculating the dipole moment of a circular ring, right? Uniformly charged with a charge density lambda. So on throughout the length or throughout the circumference, what is the charge density? A uniform line charge density lambda is present. With respect to origin, we are calculating the dipole moment. This is the origin at center O. We are calculating dipole moment of the ring with radius capital R. What is the radius of the ring? Capital R is the radius of the ring, capital R. Okay. Now, for a continuous charge distribution, the dipole moment is given by integral r prime into dq. Okay. Here dq is how much for a line charge? Lambda into dl prime. Okay. I am taking a length element dl prime. What is the charge on this? Lambda into dl prime. Okay. So dl prime can be related with the right. Okay. Angle subtended by d phi with the dl prime is equal to r into d phi. Dl prime is equal to r into d phi. Okay. Right. Where phi is the azimuthal angle you are measuring from positive x-axis. So dl prime is equal to r into d phi. And what is r prime? R prime is the position of the charge element. This is the charge element you have considered. Right. R prime is the position of the charge element, position vector of the charge element, which is nothing but magnitude is capital R, direction is r cap in cylindrical coordinates. Okay, right? Okay. So, right, okay. So assuming the ring on the xy plane with z is equal to 0, I am using cylindrical coordinates. So r cap is equal to in cylindrical coordinates x cap into cos phi plus y cap into sin phi. So now all these values are known. R prime is known to you, right? Dl prime is known to you, and r cap value is given in terms of x cap, y cap. Substituting here, P, the dipole moment of the ring is integral phi 0 to 2 pi. In place of r prime, I have written r into r prime, r cap, right? Lambda as it is I have written because it is uniform constant. Dl prime is equal to length of the arc is equal to, right, r into angle subtended, r into d phi. Lambda r square I have taken outside the integral. R cap is replaced by x cap cos phi plus y cap sin phi. X cap cos phi plus y cap sin phi. Integral cos phi d phi. X cap is constant vector. Cartesian vectors x cap, y cap, z cap are constant vectors. So taking out y cap, taking out, integral cos phi d phi, right, between 0 to 2 pi is always 0 for the total period. Similarly, integral phi 0 to 2 pi sin phi d phi is always 0. Therefore, the dipole moment is 0. Okay, for the ring shaped conductor about the center, about the origin O. Okay, right. Now, some more problems we can discuss on the dipole moment. Okay. Now I am explaining some problems which appeared in the national level entrance examination and international level exams on the dipole moment calculation of charge distributions. Here, right, I have shown a volume charge distribution which is a rod, right, which is having a volume charge density rho is equal to alpha into z minus L by 2, where alpha is a constant, L is the length of the rod, and z is between 0 and L. Okay. So find the dipole moment of this charge distribution, and second one is this dipole moment depends on the origin of coordinates. Okay. I told you already the dipole moment of a charge distribution usually depends on the origin of coordinates, but there is an exception. What is that exception? If the monopole moment or the net charge of this charge distribution is 0, then the dipole moment does not depend on the origin of coordinates. Now let us see first of all what is the dipole moment. For a continuous charge distribution, the dipole moment is given by P is equal to integral r prime, vector r prime into dq, where r prime represents the position vector of the source point, charge element, okay, dq, In this case, dq is volume charge distribution, therefore dq is equal to rho into volume element d tau prime, rho into volume element d tau prime. Here I have taken an element of length dz along the z direction, okay, at a distance z from the origin O. Okay. Now what is the face area of the rod A? Therefore the volume element d tau prime becomes A into dz. Okay. In place of volume element d tau prime, I have written A into dz into rho into z cap. Okay. Z cap. Right. Okay. So now in place of rho, I am writing this value alpha into z minus L by 2. R prime is z, right, z into z cap, okay. So z cap into, right, rho is how much? Alpha into z minus L by 2, alpha and z minus L by 2, this z as it is I have written, z into z minus L by 2 into dz, okay, right, because volume element is A into dz, rho is alpha into z minus L by 2, so alpha into z minus L by 2, okay. So here R prime is what? The vector representing the charge element. This is the charge element. So the vector representing it is this one. How much is the magnitude z and what is the direction z cap? So in place of R prime, I have written z into z cap, okay, and in place of volume element d tau, I have written A into dz. In place of rho, volume charge density, this value I have written, right, and we are integrating all elements from 0 to L. Length of the rod is L, from 0 to L. So z is equal to 0 to L are the limits. So after integrating, you will get this z cap into alpha A L cube by 12. Okay, right? Simple integration. Here it is z square integration z cube by 3, then minus L by 2 into z, right? How much? Integral z dz how much? Z square by 2. Substituting the limits, simplifying it, you will get this z cap into alpha A into L cube by 12. So therefore, clearly the dipole moment is a non-vanishing term and is directed along z direction. Okay. Now the second question, is this dipole moment depends on the origin of coordinates. Now we have to check whether the monopole moment or the net charge is 0 or not 0. So we are calculating the monopole moment q. Volume integral rho into d tau is equal to, rho is how much? Alpha into z minus L by 2. Alpha constant I have taken outside, integral z minus L by 2, and what is the volume element d tau prime? That is A into area of the element into thickness dz. Okay, integrating between 0 to L, you will get this 0. So therefore the monopole moment or the net charge of this charge distribution is 0. Therefore the dipole moment which we have calculated is independent of origin of coordinates. Okay, right. Now coming to the next question which appeared in the entrance examination, a national level entrance exam. A circular disc of radius small a on the xy plane has a surface charge density sigma is equal to sigma naught r cos phi by a. Therefore clearly it is depending on r and phi. Therefore this is not a uniform surface charge density, it is a non-uniform charge density. He is asking you to calculate the electric dipole moment of this charge distribution. Now this is the disc, right, which is present in the xy plane with the center at the origin O, and z axis will be the axis of the disc. Now as usual, dipole moment of a continuous charge distribution is given by integral r prime, vector r prime into dq. Here I have taken an element, area element on this which is having a charge density sigma, and therefore what is the charge on this dq on this area element? Sigma into dA. Now this is a circular disc, therefore I am using cylindrical coordinates. The area element with constant z is how much? R dr d phi. The area element in cylindrical coordinate with constant z on the circular disc in the xy plane, z is how much? 0. So right on this, what is the area of this element? Okay, this is d phi, okay, this is r, therefore this is dr, therefore right, how much you will get? R dr d phi, okay, is the, right, this thickness is dr, this length is r d phi, therefore it becomes r dr d phi. Okay, so now this is the area element, right? Okay, so r prime, what is r prime vector here? R prime vector, I told you, it is the representing the source. So this is the charge element you have taken. Now r prime vector is representing this. So this is at a distance r, therefore r prime is equal to r into what direction? R cap direction. Okay, into r cap direction, means r cap is the vector away from the axis. Okay, r cap is the vector away from the axis. So in place of r prime in the formula, we can write r into r cap into sigma into, in place of area, dq is equal to sigma into dA, area, right, r dr dphi I have written. Okay. Now r prime is equal to r into r cap, right, okay, in terms of Cartesian coordinates is nothing but x cap into cos phi plus y cap into sin phi. Okay. So therefore writing this value and writing sigma value here, what we will get, p is equal to r into, in place of r cap I have written x cap into cos phi plus y cap into sin phi. In place of sigma, he has given sigma is equal to sigma naught r cos phi by a, sigma naught r cos phi by a into area element r dr d phi. Okay, right. So now sigma naught by a constants I have taken out. Okay, then I have written r integral separately and phi integral separately. Under r, what we will get, r into r cube dr, r integral. Then phi integral, x cap is a constant vector into cos phi into cos phi, how much, cos square phi d phi, plus y cap into sin phi into cos phi, sin phi cos phi d phi from 0 to 2 pi. Okay. Now this is nothing but sin 2 phi by 2, sin 2 phi by 2, between the total period 0 to 2 pi always becomes 0, this integral becomes 0. Then cos square phi is how much, 1 plus cos 2 phi by 2 I have written here outside. Okay. So now I am integrating this, again this integral becomes 0 because integral 0 to 2 pi cos 2 phi d phi becomes always 0, this is 0. So you are left with this integral 0 to 2 pi 1 into d phi, that is values 2 pi into x cap. So outside this r integral is integral r cube dr is how much, r power 4 by 4 between the limits 0 to a power 4 by 4. Sigma naught by a into a power 4 by 4, a power 4 will get cancelled, a cube, sigma naught a cube by 4 into 2, 8 into x cap into, this is 2 pi. Okay, sigma naught a cube by 8 into 2 pi into x cap plus this value is 0. Therefore, finally you got the dipole moment sigma naught pi a cube by 4 x cap. Okay, so this is the dipole moment calculation of the circular disc. Like this, many problems appeared on the dipole moment calculation. Similarly, in magnetostatics also, many problems appeared on the magnetic moment calculations of different current distributions. Okay, so right, okay, with this, now I am winding up this lecture.